Hello, ladies and gentlemen. I hope you're all doing well. Root Beer here with question number 16 on our 2010 Cayley paper. The odd numbers from 5 to 21 are used to build a 3x3 magic square. A magic square is something, it's an arrangement of numbers where the sum of the numbers in each row, column, and the main diagonals all add up to the same sum. If 5, 9, and 17 are placed as shown, what is the value of x here? Okay, so it's a magic square question. These ones pop up, every now and again. I think there was one like this on the Pascal. Wonder if there'll be one like this on the format for this here as well. Now, there's lots of different ways to do magic square questions, but almost always on the contests, I find that they're 3x3 magic squares. There might have been a 4x4 at some point, but really, they're usually 3x3s. Sometimes they have a twist, where it's not the sum of the rows and columns and diagonals entries is the same amount. Sometimes it's a product thing. But if you take logarithms, it turns into a sum thing anyway. So you will often find that it might be a good idea to know the basic 3x3 magic square. And in fact, if we know the basic 3x3 magic square, we can build off of that and get an answer to this question. This is a slightly different approach to the question than I did on the 2010 Pascal paper. And so if you're interested in seeing another way to do that question, you can absolutely look up that Pascal, find the appropriate number, and go watch the video. But the basic idea with the original 3x3 is you place the numbers 1 all the way through 9 in your magic square. 5 will go in the middle. The average of the numbers always goes in the middle. And, off the top of my head, I cannot exactly remember how to fill this in. I think it's a 9 is across. 9 is across from 1, and then you get a 2 and a 4. 6 goes here, so a 7 has to go here, so 3 goes here, 8 goes here. Okay? So there's your basic magic square. Now, what is the magic square we're being asked to make? Well, it's another 3x3. And incidentally, for this, the original magic square, the sums are always 15 for every row, column, and diagonal. But now what we're talking about is, so we have 1, 2, 3, all the way up to 7, 8, 9. But we're talking about the odd numbers, so 5, 7, 9, all the way up to 21. Okay? And when we list them out like this, we can make connections that, we can actually transform from this magic square to the one that we want without changing a whole lot. How do we get from 1 to 5? How do we get from 2 to 7? Okay, you would double each number and add on 3. All right, just do 2x plus 3. 2 times 1 is 2, plus 3 is 5. 2 times 2 is 4, plus 3 is 7, and so on, all the way up to 2 times 19. 2 times 9 is 18, plus 3 is 21. But that's all we're doing, and performing this operation on each number in turn will not change the fact that the rows add up to the same number. That number will just be stretched by that same amount. 2 times 15 plus 3, so 33 will be the magic sum, as it tends to be called. So what's going to happen? Well, let's switch color here. So 2 will turn into 7. 9 will turn into 21. 4 will turn into 11. Okay? 5 will turn into 13, which is the middle of these numbers here. And we can fill this in. Now, I'm going to fill this in. I'm going to finish it off here. But it's not necessarily going to correspond exactly to the one that they gave us. I mean, I might get lucky. 7 times 2, so 7 goes to 17. 6 would go to 15. And what's the last one that we need here? Trying hard to think of it. 8. 8 is 2 times 8 is 16, so we get 19 here. Okay, so 13's in the middle. 13 times 3 gives us 39, and that is, I said 15 goes to 33, but by the same translation. That, of course, is incorrect. You multiply each number by 2, and that add on 3 3s. So it's multiply 15 by 2 and add on 3 3s, so add on 9. And so, yeah, 39 is our magic sum here. Anyways, that's not what we're talking about. We want to say, okay, here's what the magic squares tend to look like. Now, what's the magic square that they're giving us? Well, there's a 5 here, 17 here, and a 9 here. How does that compare with ours? Well, we got the 17 and the 9 in the right spot, the 5's in the wrong spot, so I have drawn sort of the mirror image, and I can correct this. Okay. So as I say, this is, I would say, the slightly faster way. I mean, I've been explaining things as I go, but this is, I would say, the slightly faster way to do the question if you're familiar with magic squares. If you're not, by all means go back and look at that Pascal paper video that I did, where I go through this question in a different way. And if there's a magic square question on the Fermat, I'll try and do that one even in a different way. So it looks like, assuming everything matches up here, the answer that I'm looking for is 7. So I've got 5, 9, 17. Oh, I've got 17 and 9 on the wrong side as well, don't I? That's okay. Quick fix. So it looks like the answer will be 11. So 11 goes here, 7 goes here. Yeah, because the 17 and 9, they're in the correct row, but they were on the wrong sides. And 19 up here, and 15 here. Okay, so our answer is going to be 11. We'll just double check. 9, 5, 17. Yep, so our answer is going to be B, 11. All right, so that finishes off question number 16, based on some knowledge, some previous knowledge of the standard 3x3 magic square. But of course, there are other ways to do the question. So that's question 16. I will see you in the next video for question 17.